Video 1 of the master course Quantum Chemistry of Molecules, Electromagnetic Properties, Introduction. Most, if not all, the experiments which we can make with molecules can be understood and therefore also theoretically described as the interaction of the molecules with some electromagnetic fields. And in the theoretical description, these fields can then be treated as a perturbation of the molecule, apart from some cases, like for example a chemical reaction, where the molecule changes identity and therefore is not only perturbed, or an intense laser field, where for a proper description it is necessary to treat the field and the molecule on equal footing. What kind of fields are we talking about? Well, it could be the static external electric field in a capacitor, or a static external electric field due to another molecule in the neighborhood. It can be the static external magnetic fields which we have in nuclear magnetic resonance or electric spin resonance spectrometers. But it also can be internal magnetic fields, meaning fields inside of the molecule due to the nuclei. Some nuclei have spin, and those nuclei also have, due to the spin, a magnetic moment, and that magnetic moment leads to a magnetic field. Similar nuclei with a spin larger than 1/2 will have an electric quadrupole moment, and this electric quadrupole moment will lead to an electric field inside of the molecule. And then of course we have the oscillating electric and magnetic fields of electromagnetic radiation. The interactions of molecules with these fields are then often described in terms of what we call molecular properties. In this course we will focus, for example, on molecular properties like the electric dipole moment, frequency-dependent polarizabilities, the chemical shift and indirect nuclear spin-spin coupling constants of an NMR spectrum, or the hyperfine coupling constants of an ESR spectrum. Molecular properties are intrinsic properties of a molecule, and not only of a molecule but actually of a particular state, electronic, vibration, rotational state of a molecule. The important point is that molecular properties are independent of the strength of the fields. They can therefore be used to describe the response of a molecule to a field of arbitrary strength. Many experiments or experimental phenomena are therefore interpreted in terms of these molecular properties. What kind of experiments are we talking about? A prominent example is, for example, the refractive index, and the molecular property explaining this or underlying the refractive index is actually the frequency-dependent polarizability. Other experiments are, for example, the Stark and Zeeman effect, which means one records spectra, rotation, vibration spectra, for example, in the presence of an electric field, a Stark effect, or a magnetic field, a Zeeman effect, and observes changes in the spectra. Kerr effect is a similar experiment. Then, of course, all the parameters from nuclear magnetic resonance spectra, NMR, and ESR, and electric magnetic resonance spectra, and many more. Furthermore, the interaction, the long-range interaction between molecules, can be understood and therefore interpreted in terms of molecular electric moments. Molecular properties can therefore be determined to very high accuracy in experiments. But why is it then interesting to calculate molecular properties? Well, I can think at least of 3 reasons. Compounds are very often identified through their molecular properties. Let's take, for example, an NMR spectrum. We identify a compound in an NMR spectrum through the chemical shifts. But this, of course, requires that we know what the value of the chemical shifts for this molecule are. If we don't know them because they haven't been measured before, we can calculate them and in this way identify newly synthesized or unknown compounds. Secondly, let's assume we want to design new molecules with tailor-made properties. Let's take, for example, color. We want to design a molecule with a particular color. The traditional way, of course, is to synthesize a lot of different molecules and see whether they have this property. A much cheaper and faster way would be to first calculate the color, the absorption spectrum of different candidates, and if they have the desired property, then we can always synthesize them afterwards. A third reason for calculating a molecular property of a particular molecule could be that we want to understand why this molecule has this particular value of this property. For example, we have a molecule with a particular chemical shift, which is quite different from the chemical shift in some related molecules, and we would like to understand why there is this change. Then if we calculate the chemical shift, it typically consists of different contributions, and we can compare those between the two molecules and often get a deeper understanding of the changes. Calculation of molecular properties can in this way maybe not replace, but at least supplement the experimental measurement of these properties. And they can provide additional important information about molecules to the energy and structure of a molecule.